This part I'm going to present is relevant to partial discharge monitoring. Good. In this picture, you can see a simplification of the electrical field in a GIS. You have here the inner conductor, the high voltage conductor, and the outer is the enclosure, and sorry for this typo, is not connected here, but is relevant to the external enclosure and the SF6 inside. And by design, the electrical feed in the GIS is homogeneous, and thanks to the insulation properties of the SF6 gas, no PD should be observed in this case, in the ideal case. But if we imagine to have an imperfection, as reported here, as a small red triangle, for example, attached to the HV conductor, well, in this case, the electrical field will change as reported in the picture and the red lines. And we will face an increased electrical field strength in the small area here around the imperfection. And in some cases, it could locally exceed the breakdown field strength of our SF6 insulation material, and accordingly can lead to partial discharge. But more in general, typical defects in GIS are due to not only imperfection on high voltage conductor, but even due to moving particles, to protrusion, to other particles on insulating surface, floating electrodes, forgotten tools, or loose or not floating electrodes, or voids in the solid insulation, and even for delamination. Here you can see that according to the knowledge rules of partial discharge diagnosis and service, according hence to the SIGRE TF 15.11, typical PD in GIS are the following. As you can see even here on the scheme, we can have protrusion on the enclosure or protrusion on the high voltage conductor here. We can have floating electrodes, as reported here on the right, or free moving particle, as reported in the SF6 in this case. And as I said, particle, for example, fixed on the insulation surface. Good. When we have PD, we have energy. This is the PD source, and these are the different type of energy, the physical effects. And we have various forms of energy. For example, we can have light, we can have acoustic waves, we have high frequency electromagnetic waves, but we have also chemical components, subcomponents as well, and heat. And this process causes a degradation of GIS components and aging mechanism that can lead sooner or later to a failure. The good news is that energy can be measured using several mechanisms, several approaches and techniques. For example, through optical measurement, mechanical, or electrical. And for this particular case, for continuous monitoring, we will focalize our attention to the ultra-high frequency method, who has shown multiple benefits in terms of sensitivity and reliability, mainly compared with the other with the acoustic and the optical method. And in particular, we will see the four main steps of the monitoring system chain: the detection, the acquisition process, the processing, and alarming and visualization. About the detection, we will have a look on the main partial discharge sensors that are applicable for GIS monitoring. The major sensor types are the following: pre-existing internal UHF sensor, unshielded epoxy spacers, or sensor for unshielded epoxy spacer or shielded spacer with small dielectric aperture, or unshielded epoxy spacer at cable termination. We have even special sensor for inspection window or dielectric glass windows that can be present on the GIS. In the following slides, you can see some picture starting from the pre-existing internal UHF sensor, and you can see here on the left, or some other example here on the right, where the majority of the modern GIS are provided with internal UHF sensor. And we can connect our acquisition system, our GEQ system, with the totality of this kind of internal sensor that can bring a lot of benefits, even in terms of sensitivity and ratio between noise and signal. This is the preferred solution where we have internal sensor to use it. But in absence of this kind of sensor, of internal sensor, we have a dedicated solution, dedicated sensor. This is our horn antenna that can be placed on the spacer and not shielded GIS epoxy insulator as reported here on the picture. The same sensor can be used even with the shielded spacer when we have a small dielectric, as reported here inside the green circle, and on the spacer. So we can use, as reported on the right, the same horn antenna, and we will see more in detail later on this other component that is connected directly to the sensor. The same sensor is applicable even at cable termination. So even in this case, we can use an antenna in this position, and in some cases, we can use a standard HFCT that is connected around the ground link, as reported here. There are different type of sensor. There are other type of sensor, but I mentioned the principal ones. The last one I want to mention is the another type of antenna that is tailored and designed to be applied on the glass windows, dielectric glass windows. You have an example here, and two installation here on the bottom left, where different diameter even of this sensor can be adapted to a different size of dielectric windows. On the acquisition side, GISNOVA system implements a dedicated unit. This is called frequency shifter, with the scope to adapt the common frequency content of PD pulses in GIS. This is normally in the range of the gigahertz, and in the most convenient frequency spectrum. With the gigahertz, we have a very high attenuation of the signal, a physical attenuation along the measurement chain. Frequency shifter is used to sort of envelope of the gigahertz fingerprint of the waveforms to shift the gigahertz frequency to a few tenths of maximum few tenths of megahertz, keeping the pulse shape that can be used later on for the data processing. And the frequency shifter is normally connected to the internal or the external sensor, and from the other side to the acquisition unit. Thanks to this approach, we can use signal cables up to 100 meters long. This can ensure a compact and a cost-effective installation layouts. About the acquisition unit, as you can see here, the acquisition unit is composed by electronic boards with a wide bandwidth electronic boards with a power supply here connector, with Ethernet port for communication and synchronization over Ethernet, and in this model up to 4 independent partial discharge channels with a bandwidth that starts from 16 kilohertz as a standard 30 megahertz, and with the frequency shifter we can reach frequency up to 3 gigahertz. These are the common frequencies that are used for GIS detection with antennas. This electronic board has a sampling frequency of 125 megasample per second and resolution of 12 bits. Here you have an example of the acquisition box, because multiple acquisition board can be mounted together in a protective enclosure for both indoor and outdoor application, or an industrial rack. So we have basically 4 PD channels for each board, 40 channels in total for each box. The channels can reach 240 when we install this kind of acquisition unit on 42 unit rack. The system, both of 240 channels, we can perform continuous monitoring. So the system is capable to perform continuous acquisition and monitoring, and even simultaneous acquisition on trigger events. The system is capable to be synchronized in the range of 0.1 Hertz up to 1 kilohertz. So it can be utilized even during the GIS commissioning with an external power source, and the frequency far from the nominal one, 50 or 60 Hertz. We have the possibility to utilize 66, IP66 or 68 for outdoor application enclosure, and with extended temperature range from minus 40, 45 up to plus 60 or 70. And on the acquisition unit, we have embedded OPC UA 62541, 61A50, and dry contacts protocols. So we have a multi-protocols device. And here you can see an example of a layout using 4 acquisition boxes connected to each other by a fiber optic to the central unit. So we can reach easily configuration with hundreds of PD channels. Looking to the processing, just a quick step back for the definition of partial discharge. We know that partial discharge, according to the definition of the IC standard 6270, are localized electrical discharge that only partially breach the insulation between conductors, and which can or cannot occur adjacent to the conductor. On the bottom, you can see a common way to represent PD. This is the phase result PD pattern. And on the horizontal axis, you have the phase angle. On the vertical axis, the amplitude, and even different colors according to the number of pulses acquired per each cycle. It's important to mention that based on the PD pattern, the defect identification can be carried out, since as you can see in this animation, different defect typologies forms different PD pattern shapes. Identification is always is a crucial factor in the PD assessment in general and even in the GIS application. In general, we have to consider that normally internal PD are more and more dangerous than surface PD. Here, the second category, and again, surface PD are more and more dangerous back to the corona discharge. However, when we move to this ideal case or the theory and move from labs to real cases, diagnosis is normally not possible with standard device. As you can see here on the graph, high level of background noise is in online monitoring can hardly affect the results, and apparently only noise is visible. This is our main innovation. We started more than 20 years ago to develop a method to reject the noise for online application, to be able to identify the partial discharge source in online conditions. This is again the fundamental innovation. So for each pulse apart, we create through a mathematical calculation. We calculate other two parameters, equivalent time and equivalent frequency. We create another map. The name of this map is classification map. In the classification map, you can identify and we can clusterize the phenomenon, and we can easily identify different cluster, different group of points, colored in this case in black, red, and in blue. And after this classification and clusterization process, the system is able to rebuild the PRPD pattern only for each separate homogeneous group of points. And this is for the red one, for the black, the red, and the blue one. And this approach is very useful when we have to test or monitoring in GIS, because multiple PD sources can be even identified below the background noise. GISNOVA, our model for PD monitoring in GIS, implements the TF map technology and analysis, and which allows an effective separation of even different multiple sources. Here, just to give you an example of the processing capability in GIS application, here we have, after noise rejection and PRPD pattern, that shows some points. Here is the equivalent time frequency map, where we can identify two main clusters. One is the black one, where we have an HV protrusion type of defect that can be identified using even the database and the fuzzy logic algorithm, and the red one with the floating electrode. So in this case, we have two combined sources of PD. The system is capable to separate different phenomena and gives different alarms in this case, or in other case when we have multiple PD activities. Some additional info about PD. We have here a typical PD pattern for protrusions. Protrusions again are caused by bad assemblies, stretching and of parts during service life operation of contacts, and etc. There are two types: protrusion on high HV conductor, the more dangerous due to the high field, or can be on the enclosure. Or we have even here a pattern relevant to free-moving particles. Free-moving particles are one of the most frequent and most dangerous defects inside the GIS. Due to a lot of reasons, they provoke a distortion of the electrical field. As we said, we can lead to PD. Even charged particles float and can move due to the electrostatic force inside the compartments, and can be provoke failures in few weeks.